Okay, let's talk for a moment about factoring sums and differences of cubes. So as soon as you realize that you can take an expression like x squared minus y squared, a difference of two squares, and write it as a product of x plus y times x minus y, and use that in lots and lots of different places when you're trying to factor expressions, one's naturally pretty curious about what would happen if you just, say, change that 2 to something else, like, say, a 3. What if we looked at a difference of cubes? Does that also have a nice factorization that's not necessarily obvious just by looking at this, right? There's no common factors here. There's not many terms to work with at all to kind of go backwards to some sort of factored expression. But sure enough, if you play with it for a little while, that's not too bad, you can break this into x minus y times x squared plus xy plus y squared. Okay, a little more complicated than its cousin here, a difference of squares, but not too bad. Okay, and further, because we're talking cubes, you can use this same form here almost to find the sum of cubes as a product. The only thing really that changes is this sign here, x plus y, and this sign here. So we have x plus y times x squared minus xy, and again, plus y squared. Okay, so these two guys here are very, very useful to kind of commit to memory so that you don't have to go through playing around, inserting what terms you need, compensating for your insertions until you can break it into this. We just remember this form and we can use it over and over again whenever we see a difference of two cubes or a sum of two cubes. So let's take a look at a couple examples to that end. First example, 27 minus x to the sixth. Okay, so the first thing we want to ask ourselves is it even is it a sum or difference of cubes to begin with, right? We don't want to apply this in the wrong situation. So certainly it's a difference. We have a subtraction there. Is the first thing a perfect cube, right? That's what we have in both cases here. Sure, 27 is the cube of 3. What about the second thing, x to the 6th? Can we cube anything nice and get x to the 6th? Sure. X squared cubed would give us x to the 6th. So that establishes it as a difference of two cubes, right? Which means we can write it in this form here. Whatever we cubed to get the first term minus whatever we cubed to get the second term. So we have that difference times, let's see, this is this x squared, right? So whatever we cubed to get the first term squared. What do we cube to get the first term? 3. So this is going to be 3 squared, or 9. This is the product of the two things we cubed. Again, the two things we cubed were 3 and x squared. 3 and x squared. So the product of those two things is just 3x squared. And this guy here, that was whatever we cubed to get the last term in our difference. What did we cube to get this? Oh yeah, that was x squared. So if I take that and square it again, I get y to the 4th. Okay? And barring being able to factor this or this further, which neither one factors any further, we have a complete factorization of 27 minus x to the 6th. We're done. See how fast that is if you know this. If you don't know this, if you haven't committed to memory, then playing around with this expression is going to take a whole lot more time. So this is one of those few cases where it's really, really important to go ahead and commit that to memory. Let's look at a second example. How about 8a cubed plus 64b cubed? Okay, so here again, let's make sure we're in the right ballpark. Is this a sum or difference of cubes? Well, it's clearly a sum. The question is that something that represents a perfect cube? What could we cube to get 8a cubed? Well, it's pretty clear we're going to need an a. And to cube something and get 8, we must be talking about 2. So 2a would work there. Is this the perfect cube of something? Something nice. Well, here again, b is probably involved there to get b cubed. What can we cube to get 64? Well, probably 4, right? If you know your powers off the top of your head. And it's a sum. So we have a sum of 2 cubes. This equation applies, right? The x here, again, is what we cubed to get our first term. What do we cube to get this? This, right? So this is playing the role of our x. And the y is whatever we cube to get the second term of our sum. What do we cube to get this? That was our 4b. So this is playing the role of our y. So x plus y is that. And over here, x squared. Let's see, x was this. So squaring that, we'd have 4a squared. Minus the product of x and y. So minus the product of those two things. So minus 8ab. And last but not least, plus y squared. That's this plus 4b squared, which would be plus 16b squared. Okay, so I now have a factorization of 8a cubed plus 64b cubed. That said, I went about it in kind of a silly way. All right, the next question I need to ask myself is, do these things factor any further? All right, and sure they do. Look at this one right here. Immediately we see there is a common factor on those two terms of 2. We would have been better to pull out any common factors as the very first step in trying to factor this expression. That will keep our numbers small. It's not to say you can't do it this way. We did it. Everything's fine. We can keep going with it if we wish. But if you want to have smaller numbers and ergo solve the problem faster, look for those common factors first. So let's do that. Okay, let's restart this problem, looking for our greatest common factor we can pull out first. That'll get the numbers down. This is something you should always do when you're trying to factor an expression. Do that first. Looking at these two terms, both of these terms are divisible by 8. Let's pull that 8 out right now. So we have 8 times a cubed plus, let's see, 8 times something gives me 64b cubed. I bet it's 8b cubed. Now we can say, well, does this factor any further? Now we can ask the question, is this the sum or difference of cubes? It's clearly a sum. That's clearly the cube, namely of a. So x is playing the role of a here. This is also clearly a cube of b times 2. So 2b is playing the role of y here. We do indeed have a sum of cubes. My 8's coming along for the ride. And then I'm going to have the sum of x and y, the sum of a and 2b in this case. And then over here, my x squared, remember my x was being played by a in this problem. So I have a squared minus the product of x and y here. Again, this is my x, this is my y in this problem. It's whatever I cubed to get those two terms. So the product of x and y is just 2ab. Notice I wrote that with the 2 in the front. That's to be somewhat aesthetically pleasing, right? From simple known things to more complicated unknown things. But it's the same product. And then last but not least, plus y squared. So plus this guy squared, that would be 4b squared. Okay? And notice how much cleaner and faster that was. Kept the numbers small. When you're trying to factor, let me reiterate, check for greatest common factors amongst all the terms first. Pull it out if you can, and then keep going. Okay? All right, so that was 2 examples of factoring sums and or differences of cubes.